Okay, hello everyone. We're very delighted to have you here to join us with this first Hangout on Air for today. And we have Professor Jeff Kramer with us live from London, England. So Professor Kramer has the distinction of being our long distance record holder for our Hangout. So we'll introduce him in just a moment. So I'd like to mention that if you're following the MOOC, we had a release of the midterm exam just recently, so please look at that. Some of you have already completed that. And we've also released the next lesson on abstraction just recently. So please check that out, and that's also on Piazza. We also announced some extensions to the deadline for the Create Performance task at the end of July, and we'll also work with anyone who needs a little more time. It just means that we'll be a little delayed in getting the certificates out to you. So we've had some requests for those extensions, and we're certainly willing to work as needed. So please keep in touch with us on Piazza, and we'll continue to release the lessons from Unit 4. Next week, several of us from the instructor side will be in Austin, Texas at the CS Principles pilot meeting, and there's likely a lot of information that will be revealed there. And as much as we can, we'll make sure that that information gets out to you. That could be changes to minor changes to curriculum frameworks or performance tasks or some other things that I won't know until next week, but we'll certainly let you know as much as we can what changes are coming up to CS Principles. Okay, so I'd like to introduce Professor Jeff Kramer with us from Imperial College in London, and Jeff's very well known in the software engineering. He's been the editor of the Transactions on Software Engineering and ACM's TOSM as an associate editor, so he's worked a lot in software engineering. Well known. He's even a fellow of many different societies and organizations, including a fellow of the ACM, which is one of the top computing societies. So very distinctive researcher to be on with us. And in the CS Principles pilots and others teaching this course, his paper from several years back about the role of abstraction in computing has been read by many who are preparing for CS Principles. In fact, you're reading it as a part of this course here. So this past May, I was in Italy at a workshop, and I looked back, and there's Jeff sitting behind me, and so I thought, hey, it would be really neat to see if we could invite Jeff to come and speak to us about that paper and any other ideas that he has on abstraction. So I'm going to go ahead and pass it off to Jeff to say some words to you all. And as you would like, please post comments out on Piazza, and we'll bring those back over into the chat window for Jeff to consider. Okay, Jeff, can you go ahead and say a few more words about abstraction for us?
Yeah, sure. Sorry, excuse me. Thank you very much for that introduction, and thanks also very much for the invitation. It was really quite exciting to be invited to do this, and so I'm delighted to have the opportunity. As I said, it's actually very gratifying that the paper has actually had this kind of, I don't know what to say, I don't know whether it's fame or notoriety, but whatever it is, I'm glad that it's actually made it out to all of you. One of my colleagues previously talked about research as being a little bit like putting messages in a bottle, and then you throw them into the sea, and who knows what shore they're going to land up on. And when Jeff told me about it being read by all you guys and the teachers and being, in some sense, a special area within the curriculum, I was delighted. I mean, it's very nice, and so what I tried to do this afternoon is to give a little bit of background to sort of, first of all, why I wrote the paper and what it's about. So first of all, some background. Then I'll give you some current thoughts that I've had since the paper, and I think related to what I've seen and what I've discussed with Jeff. And then lastly, we can just open it up for questions and discussion. I'm happy to try to answer anything, and if there's anything I don't know, I will, believe me, say so. So perhaps the first thing to do is to just talk a bit about the paper and how it came about. I mean, I've been teaching computing and computer science and software engineering for a long time, I hate to say. And it just occurred to me from all my experience that there was such a huge disparity between the abilities of various students. And I was trying to work out what it was that made the good students good, the bad students not so good, what it was that made them, some produce beautiful, elegant solutions, and others just seemed in really following some of the complexities and some of the niceties of algorithms, of data structures, of models, and so on. And in thinking about this, one of the things that came to me at the time really was to do with it seemed to me that abstraction was the key to this, that the notion of being able to form some higher level description, some abstraction from reality or from some complex problem, and reduce it to some elegant, neat, understandable algorithm, technique, model, whatever it is really an ability which some seem to show and some did not. And so abstraction seemed to me to be the important key. So the next thing you really come across is, what really is abstraction? And most people have this kind of vague notion that they'd recognize it when they see it. It's a bit like elegance. You know it when you see it. But trying to describe it and talk about it is not so easy. And so abstraction is really partly this process of getting rid of the clutter, the detail, all the bits and pieces that you say, well, I don't really need to talk about the color of this object. I don't need to talk about the way it moves. I only need to know when it does this particular event or when this happens and so on. So you select out those parts that are important and you discard and ignore all the parts that are not important. And this gives you a higher level of description and abstraction from whatever it is. But this is only one of the aspects. The other is trying to find the core, what I call the real common meaning of something, of some element, some part. And so this notion of looking for this essence, I also try to describe in the paper. Now these are all parts of abstraction, and I think some students get the notion that they need to describe things in terms of simpler entities or simpler actions, and others include all the detail and all the clutter, and you can't see the wood for the trees. But the other notion is that they have to be inventive. Creating abstractions is actually creative. It's the notion of choosing which are the things that are important and which are not. And for that you need purpose. You must do, an abstraction actually has and is created for a purpose. And so you might have different abstractions for different purposes. So the notion of having the abstraction, for instance, if we had a bridge, you might create a physical model so that you can look at the aesthetics, and that's the purpose of that particular physical model of the bridge. But that's not a good model. It's not a good abstraction if you wanted to work out stresses and strains. Then you create a mathematical model with all the stresses and strains and differential equations and so on. And that's a different abstraction, and it's good for working out whether the bridge will fall down, but it tells you nothing about the stresses and about the aesthetics, whether it look good in that particular location. So purpose is I think, a very important part, let's say, of choosing and working with abstractions. So I try to describe this in the paper, and I think one of the examples I came up with, which I really recommend to you, is the London Underground map, because this has become an iconic form of describing whether it's the New York subway or the Tokyo metro system. And it didn't start like this. You have to realize that originally they took an ordinary map, a physical geographical map, and overlay metro, the subway system, the tube system on top of that. So it looked like a geographical map. And this was really the insight of an individual, in this case a guy called Harry Beck in 1931, who came across the fact that, or said that this is too complicated. There's all this clutter, all this unnecessary detail there. What you need to know is which line connects and which station connects to which other one. And so he simplified the map down for a particular purpose. And so the big thing here is to be able to test your abstractions, to be able to look at abstractions as to whether they are fit for purpose. This is a standard engineering assessment and test. is this description, is this model fit for purpose? And in this case, all of the various maps that we now have of underground systems follow exactly this kind of abstraction. And however, it's not a good abstraction if you want to walk through London. And many people are misled by the fact that some stations, although they look close to each other on the subway map, they're not anywhere near each other. So abstractions, as I said, an important aspect of this, which I find ignored in many cases in discussions, is purpose. One of the questions which has come up, and I can already see it as one of the comments, is to do with can we teach this? Now, I can only work on anecdotal evidence. My feeling is that yes, we can. We can certainly improve our students' ability to work with. And finally, I think the final test is to create abstractions. So working with and understanding abstractions is the first part. The second part is to be able to create them yourselves. And this is a bit like I can read a program and understand what it does, and the next stage is to be able to write them myself. And abstract. So you're creating abstractions whenever you write programs, whenever you come up with algorithms, whenever you come up with data structures. These are all abstractions of some reality. Now, is it teachable? I believe so, and I believe the best way to teach this is through lots and lots of examples. It's very hard to say we're going to have a course on purely just abstraction. You teach models, you teach it in programming, we teach it in all different ways. But in each case, we hope that we're improving the ability of our students to actually use and recognize abstractions. The additional thing which I think we really do is that we don't then talk about them as abstractions. So I think a bit of reflection that having created something is to discuss with students, to discuss, is this a good abstraction? Does it represent the aspects that we're interested in? Can I test it? Can I ask it questions? Can I reason with it for the purpose that I want? Or is it a bad abstraction? Is it actually not good for the purpose? And so I think talking about abstractions, discussing them, getting students to recognize whether this is more abstract or less abstract are important. But the most important part is it suitable? Is it fit for purpose? And I think that's something we can do. So lots of practice in modeling, and when I say modeling, it can be anything from physical models to mathematical models. We have a lot of models in software engineering, a lot of formalizations and so on, and that's mostly what we as software engineers do. We create the formal notations and so on, the mathematics, and then the practitioners use that to create their models. And both of these are creative aspects, and both of them are using abstractions. So I think this is the only way that we can actually do it to improve is lots and lots of practice. First, as I said, just using abstract models or abstractions, and secondly, the next stage is to create it and assess them. I also discussed a little bit about the research we're doing in trying to assess a student's ability at a particular time. This is partly to be able to actually correlate it with what we think good students really do have, let's say, and do score highly. So if we could test abstractions, would students who we consider good, would they score highly in these tests? Now, these tests have not been easy to create, and we're still working on them. And the other aspect is one could then actually choose, I mean, if you're employing someone or you're accepting students into your courses and so on, what you would like to say is this particular student, they may not have done so well in other academic subjects, but do they have a real flair for abstractions, in which case they may actually be very good computing people and software engineers, even though they may not be good at academics or standard mathematics even. So that's my general thoughts on the subject. I would say that a few things one could look at in abstraction. One is to recognize it when you're using it. So levels is important, but for me it's not the crucial part. Recognizing what is an abstraction, when we take, let's say, an elevator, you know, what what would I want to do if I wanted to model an elevator? Well, I need to recognize that I'm throwing away, the color of the doors. I'm throwing away perhaps the time it takes to move between floors, and I'm going to concentrate on the buttons and entry and exit so that I can check that not more than the recommended number come into my elevator. So you have to work out what it is you want, and then you can actually go on and work with it. So recognizing abstractions, working with them, inventing new abstractions, ensuring that they are fit for purpose, and finally recognizing that you must map from your abstraction to the real world. So what you've thrown away you're going to ignore, and that when you make some results or you work through your model or your abstraction, that you can map back into the real world. Perhaps it's time that I kept quiet now and shut up, and then what I can try and do is I'm happy to answer some of the questions. I can see a lot of questions coming in, but I'm not quite sure I can read them all and answer them all. If I have a look here.
So I will be happy to read the questions out to you.
Please go ahead. I think that would be the best, Deepa. That would help me enormously.
Great. So Margaret Todd says she loves the creativity of the early years link, which is at the bottom of your page that we all have read. Just so that you know, we were all given a reading assignment, anybody who is in the MOOC, and all of us faithfully did, so that we could follow your talk today, which I think is very interesting. I've taken a lot of notes myself for my class. There's a question that Margaret Todd continues to ask. In the program, I could use some clarification on abstraction. Here are 3 ideas I have. In the programming language Alice, if I take an object like the ice skater and I program her to perform a triple axel and then save the ice skater as a new object, is that abstraction? I will stop there and she has other questions.
I don't know is the straight answer. In the sense, perhaps I can describe it a little bit like this. I'm not quite sure if I'm understanding what Margaret's intending there, but what happens, let's say, if I was filming this ice skater, I'd have to say, what is it? And then I wanted to save and program or reason about what is a triple axel, exactly what the movement is. I don't need to know what dress the skater's working. I don't need to know certain attributes of it, but I might be very interested in exactly how the skate, and I might be very interested perhaps in the overall body movement. Now, if I reduce that into, let's say, a form that I could then store in the computer, I could compare various people doing triple axels according to exactly the way the skate, whatever it is that purpose was. That is clearly an abstraction of somebody actually doing it. So the film of somebody doing a triple axel has all the detail in it. But if I wanted to analyze that and reason about it, I can't do it with all of that detail. So I create this abstraction, concentrate on the pieces I'm interested in, and reason about those. If that's what I did and I created this object which stored only certain attributes, certain parts of that movement, that's clearly an abstraction. I hope that helps. I don't know.
I think so. I think that's a fantastic way of putting it, and I'm sure Margaret will post further questions or clarification concerns on Piazza, which we 3 will be glad to grab for you, Margaret. Thank you for these amazing questions. Her second question is, for an unplugged activity to describe abstraction, if I send the girls to the main office, the idea that they get to know how to get there without directions, is that abstraction?
Again, not in itself. If there's an entire, that they walk through and they do let's say a search, an exhaustive search of the school or campus or whatever it is, and to find, let's say, the main office. If I describe that as an algorithm, as a strategy to get there, then that is an abstract point of view. In other words, I haven't described all of the things they're going to see, but I might describe, for instance, you know, go to the door. From the door, you walk along a passageway. You know, at the end of the passageway, there's this. Again, I've reduced it to a description. And if I use that description is more abstract than the full possibility. Now, often what you would do is if I had a robot, you know, some kind of robot that I wanted to program to do exactly what she's described for her girls, I cannot assume the intelligence that they have, and therefore I would have to include a more abstract description and algorithm for that robot to recognize particular parts of the, let's say, the route that they need to take, or route, sorry, in America, and they would have to, also have some strategy as to how to move in order to get there. So it has an objective, an algorithm which is perhaps exhaustive, or one which describes explicitly, look for the door, look for this, look for that, move to here, move to there, and so on. Software and algorithm, all of these are abstractions of what people normally do, which has all of this detail. And people naturally choose. We naturally look for particular things and ignore a lot of detail which is around us. We cannot rely, when we start to create software, we cannot rely that it will know what to look for. We do it quite naturally, but when we create software, we have to create these abstractions and be able to tell it what to look for.
Excellent. I'm going to take another minute to go ahead and a minute of your time towards the same set of questions. I'm going to combine these two. So Margaret's third question was, in the snap performance task, so I hid all my declared variables under a block that I made. Is that abstraction? That is, all the coding that is done to pull out the underground lines, is that abstraction? That gets separated into a subroutine or a block. So to translate what Margaret's asking, she was given a task assignment in a block-based language, and she took all the variables that she had to declare and she hid it underneath. Anything that has to be the fundamental stuff that needs to be done, that's what she, I believe, means by underground lines. If that is hidden underneath something, into a block, hidden underneath a subroutine, would that be abstraction, is her question. And this is her final question. Thank you, Margaret, for some outstanding questions.
Yes, thank you very much, actually. They're very interesting. I think that the notion where you are taking, let's say, some either procedure, or in this case, let's say it's data, which describes and has more detail inside it, and providing a more abstract view at the interface to this block, so that you're dealing with it in a more coarse-grained level, means in some sense that it is more abstract than the detail which is provided inside there. So it's quite true. What happens in a lot of software and software engineering, for instance, is that we work at a very high architectural level, in other words, an abstract level, where we assume that large chunks of activities can be performed, and that we will find a way to solve those sub-problems. So the high-level view is more abstract and describes the problem in pieces which are much more coarse-grained. And then if you go inside one of these boxes and look inside and see all the workings, that's clearly got more detail inside it, describes how to achieve that particular objective, and is, in that sense, less abstract. And so you can work all the way down. Certainly one of the parts of these activities known either as abstraction and the counterpart, which is refinement, work together in software and software engineering. So yes, it's an abstraction. As I said, people work naturally with abstractions. Some people more naturally than others, though. But yes.
Great response. Thank you so much. And I have to tell you, sir, you're generating a lot of traffic. This is phenomenal, the kind of questions, the quality of questions, and the interest that this particular session has taken.
Right.
For first thing in the morning on Thursday, we are doing great. Dr. Sean Parsons had a question about tests, and here it is. Have tests been developed since the time of you writing the paper to successfully measure students' ability or potential in abstraction?
That's it. That is exactly what we're trying to do. That is exactly our aim. Unfortunately, I can't say that we have. What we've done is we're still trying to see exactly how we can test this out. Abstraction is generally used as part of the tests. As you can see, I'm not a cognitive psychologist or any. I've just looked into it just for my own interest. But it seems that abstraction is an ability in general, and so there are a lot of abstraction tests which are included even in IQ tests, intelligence quotients tests. But these do not seem to be exactly the same kind of abstraction as we talk about in computing and software. Somehow, I don't think, and there's a colleague that I'm working at, her name is Orit Hazan in the Technion in Haifa, and she's actually an educationalist rather than I'm just a computer scientist and a software engineer. So she's and I have been trying to work together to tailor a set of tests. And so we created a questionnaire first to try to ask people what they thought. And so we have some idea of these patterns of tests. To be honest, I'm not yet happy with them. I think there's too much emphasis on level. And I think level is not actually the most important aspect. I think the much more important aspect is purpose, the ability to reason and use the abstractions to ask questions, and to actually be able to assess them. So you know whether is this, as I said, a good abstraction, a poor abstraction for that purpose. And then ultimately, the big test is, can you create an appropriate abstraction for some particular purpose? And so I think a set of tests along those lines is somewhere we're working towards. But the straight answer is no, we're not there yet. But we're happy to have others who put comments in and contribute.
Always for the good of the community. Amin Lalani wants to know if there's any correlation between mathematical capability and abstraction. And after you answer that, I have to share how we've had audience participation on this question. But the question right now on hand is, any correlation between mathematical capability and abstraction?
Right. I have a feeling that there might be, but I'm not sure that it's as strong as one would think, given abstraction and the notion of being able to do symbolic manipulation, hypothetical reasoning, and so on are all good things for mathematics. But somehow, I mean, from a personal point of view, I'm actually not a good mathematician, but I think my abstraction abilities are pretty good. So I somehow have this feeling that there is something else going on. And if we could develop these tests, of course, we could answer her question very well. I mean, I think that's a very good question, as were the previous ones. But we could then actually try to see whether there is this strong correlation or not. In the same way as we would want to see, is there a correlation between the tests and what we believe in terms of, computing and computer science students and even practitioners? Does it correlate with that? So it's a good question, but we're not there yet. But I think there's less than one might suspect anyway.
And so Daniel says, perhaps abstraction ability is likewise not so hardwired and can be grown and developed with. And he refers to a group led by Joe Boaler at Stanford, who sees much more potential for math growth. And I think real question here that's relevant to us is that maybe abstraction is more like an ability and not like a gene thing.
I think this goes with the is it teachable kind of question. And so, can we develop these? I think like most things, some people have greater innate abilities, but I honestly believe that we can and should and actually be able to teach it, and we should teach it. I think for me, it's not only important if you want to become a computer scientist. I think it's not only important if you want to, do software engineering and so on. I believe that the notions of dealing with abstractions is actually quite important in life in general. Being able to deal with complex situations, whether it's family situations or whether it's politics or legal situations. I think that the ability to be able to reason and come up in some sense with ways of describing this is probably one of the most important things you can do in terms of taking leadership in any facet. So I think that although I'm concentrating and we're very keen on abstractions and abstraction abilities and the teaching of it, let's say for software and for software engineering, I believe that it actually has wider implications. I think it's a very important skill. And the better you are actually at doing this, I think that you can perform in many aspects of life in a better way.
Great. I think you did answer this, but I'm going to just read it out. But I believe it's been addressed in several ways here. Is abstraction and separation of concerns the same thing? Or does abstraction represent a concept that allows separation to occur?
Wow. Straight off my head, I don't know what to say. I'm a great believer. Separation of concerns is very important. I mean, it's exactly what you need to do. So you're quite right. There does seem to be this very, what can I call it, this relationship in the sense that in separation of concerns, you are literally making yourself concerned about one thing and not concerned about other bits and pieces of it. So in order to deal with a complex problem, you basically are looking at different parts of it as different concerns. And I guess that if you swap the word concern for purpose in the same way, it's what we're doing with abstractions, because what we're doing is ignoring a whole lot of detail over there so that we can concentrate on these concerns or this purpose here. So I would say there's clearly a strong relationship. When you do it, are you performing abstractions? I guess you probably are. I would not like to be pedantic about it. It's a good question and a good idea, but certainly it's part of exactly what you need to be able to do if you're going to do problem solving and so on, is separation of concerns. So yes, I must admit I haven't thought about it quite like that.
And you never, with this kind of a crowd that we have here, they keep us on our toes, don't they?
Yes, great.
Yeah.
It's great.
It's an exciting morning, I have to admit. A very, very exciting morning. Jonathan Corley, our PhD student online with us here, he has a question for you. Does your idea of question patterns for abstraction lead students down a particular path through the lens of the instructor?
That's also a good question and something I would worry about. I mean, the intention anyway is not to try to narrow the focus, or the intention of the patterns was to try to see whether they made sense, to get some assessment from the community, and then to create an actual instance, in other words, actual questions with real examples illustrating them, and to ask them about that. It is very much oriented at the moment towards, I would say, computer science students, people who understand the field well, and practitioners. It's not aimed at the general public, I would have said. Is that a good thing? At the moment, I must admit, I don't know. I think what I would like to be able to do is, when we're happier with those patterns, is, as I said, to create one instance with a set of questions, to run that set of questions, and to actually start to evaluate whether it's telling us interesting things or not, and whether it correlates with some of the things that have been asked here with mathematical ability and with, let's say, ability in a computer science course. And whether it's too narrow and whether it leads you down just that thing, I would, as I said, that's certainly a danger and something I would try to avoid. It's a good point. It's a good point.
Great. Another one from Jeff Baker. So Jeff Baker is one of our teachers in Alabama, our teacher leaders who's been teaching CS principles.
I'm always happy to have another Jeff.
and also a very experienced teacher. So he has already taught abstraction for high school students. In explaining abstraction to students, would talking about common icons that high school students are familiar with, Twitter, Chrome, Facebook, be a valid way to start a conversation? Do you have any ideas on top of your head about how to transition into getting students to start developing their own abstraction?
I think you can talk about any of the pieces of software, whether it's a web browser like Chrome and so on, or whether you're starting from scratch and saying, I need to program let's say a cleaning robot to clean my house. What are the things that the robot would need to know? Where does it need to go? And what kind of movements would it need to have? So that students start to think about the fact that how to create abstractions, but also, one of the things that I find troubling, at least in my own, is most students think that the software and the interfaces that we have came from nowhere, or they just, Microsoft defined them. The keyboard or the mouse or each of these things has come by some great insight by an individual who came up with a notion as to how to make that interaction simple without being cluttered with all sorts of unnecessary movements or whatever. And so the notion of even the cursor on a on a screen, each of these ideas has thrown away all sorts of other bits and pieces that could have been an interface. So if you think of a camera facing me and I had to point to say where everything has to go and so on, that's very nice, but you have to be able to say, ignore certain parts and look at only where that finger is. Now, I also need to know when not to look at the finger and so on. So the notion of a mouse is actually a brilliant idea in terms of a way of interacting, rather than as we used to with a keyboard, have to move up and down lines and move across and so on. So all sorts of insights come from looking, I think, both at history of software and at current software, at what they allow you to do and what they think are important parts. And I think comparing them and so on is also very useful. It's not, I wouldn't say it's easy, because I think understanding what abstractions is in the beginning is quite hard for people to think about. But I think the notion of models, even physical models, you see architects' models, is a good way to start and to say, well, isn't that good to see the way people will move through this building or move through a school or a hospital? But is it ideal to do the wiring? Is that the kind of model you would create? Is it going to be a good model to see the way patients move through the hospital? Maybe yes, maybe no, and so on. So you have to think about what it is that they want to do with these. So I like the idea of creating models, for me, of something. But I think there are lots of starting points, and I think that starting with existing software is also, and analyzing it as to what is it good for the purpose that it's created is also a good thing to do.
Great. That's a fantastic answer. It really helped me understand how I can do this in my K-12 classroom. Thank you. And thanks, Jeff, for the question too, Jeff Baker.
Yeah.
Leandra asks, Your examples from art and music of abstraction are Matisse's abstract nude and aspects of jazz. Can you think of an equivalent example of abstraction from either literature or film?
Wow. I suppose from film, so just off the top of my head, the only thing I can think of at the moment is a lot of animated movies are, in some sense, more abstract than the real world, that they don't put all the detail in there. However, because we're very visual entities, people use their eyes a lot as a way of absorbing information. Actually, if little details are missing, if people don't move the right way, you notice it immediately. So there are some things which are crucial and some things which are not. I don't know if that's a good example, actually. Film, literature. Even in literature, I guess you could argue, no, I don't know if this is a weak argument, I guess you could argue in literature that the story that people are telling you, let's say you write a biography, you actually are selecting from your life those parts that you believe would be interesting or that you want to make a particular point, and ignoring all the boring detail about brushing your teeth or cleaning the house or anything else that you do. So you are being selective. So there is a notion of abstraction even in writing a book, because you're being selective. Now, is it, I mean, and I guess the purpose there is to be interesting to the reader, so you could assess your abstraction as to whether it achieves that or not. It's less, let's say, scientific, mathematical than the kinds of things we deal with, obviously, in software, where, let's say, the assessment of goodness of an abstraction is much more according to whether I can test something to ensure it doesn't fail, or that it will actually control the aeroplane, flying. So this is a much more subjective value judgment kind of purpose for this abstraction. But I guess one could make that argument. But it is weaker. I can see that.
Weaker or not, definitely it's helpful. At least you're right. Writing a book is some form of an abstraction, so that's definitely a very helpful one. Though, anytime you do art or music, they are very valid examples, and they get the message across much more quicker than a motion movie or abstraction. Yeah. So I can see the value in why you would use that as an example in the classroom. We had a follow-up question from one of our audiences, and I'm going to, Timo, you've got to forgive me. I'm going to rephrase the question a little bit differently to the best of my ability of how I've understood this. Piggybacking a lot of things that you have said, Mr. Kramer, Timo would like to know if factoring of trinomials, would that be a valid way to teach abstraction, where you could use that and give examples to help students formulate patterns as they think through it and be reflective about it? Clear?
Yeah, no, I understand. I'm trying to. For me, I would say that would be a less motivating, weaker form, in the sense, in mathematics you can perform and do all sorts of different, let's say, I don't know, various manipulations, equations, and so on. I'm not sure that it teaches, other than practicing this notion that you can live and work in a world which may or may not be related to reality. In other words, that people are comfortable doing that. I think that the abstraction that I'm more interested in, and I think that relates anyway to, let's say, computer science, means that you need to retain the link to reality, the link to the real world. So this mapping to and from the real world. So if you were performing this factoring, and it was because there was some problem, some real world problem that you were trying to solve, and that this was a way of essentially capturing the essence of that problem, then I can see it as a very good technique. If you do it in isolation, I would say I would be less encouraging. So it's very good to be able to manipulate, and I actually argue even in the paper that having a mathematical background, sorry, this is my phone. Having a mathematical background is certainly helpful in teaching you how to manipulate symbols. But I think that for me it's much more important to retain that mapping, that link to some reality, and recognize that what you've done is abstract from some real world or something into that model, manipulate in the model, and then take the implications of that result back into that real world.
Fantastic, thank you, and thank you for picking on. I was a little concerned if I was able to convey it, but you did a great job, sir.
No, that's okay.
So Mark Woodward asks, I'm searching for some analogies for abstraction. It seems like that there are two main areas to abstraction, much like nouns and verbs are to language. One part is like nouns, how to represent the objects through data structures like lists, arrays, trees, etc. The second part is like verbs, how to manipulate the objects through methods, algorithms, etc. Am I on the right track?
I would say partly. If you're talking about software, and you're talking about programming and so on, and trying to create it, certainly there are these dual aspects of the data, the things that you actually hold the information, and then the procedures which actually move through them in a particular way according to what it is you're trying to achieve. And that's often called the algorithm or the strategy, or, you know, in cooking, that's the recipe. So the ingredients would be the nouns and data structures, and the recipe would be the algorithm or the actual process. Now, is that in each case they are using abstractions, but is it actually an abstraction? Well, in the case of the cookery, not much, because the description is of the particular items. If in the data structures, yes, each of those is an abstraction because you are representing some real world, some part of a system by, you know, integers listed together to represent, you know, whether it's individuals. Let's say, you know, you've got 30 students in your class and you give each one a name, and then I have a linked list of each of their names and so on. I'm using that to represent those individuals. I'm also using perhaps the marks that they get in their mathematics course and so on, but I'm ignoring all sorts of other objects or other details about them. So for the purpose of the mathematics class, that's a good data structure, and then I might manipulate them to find the average and so on. But so you're using abstractions, but I don't think those are necessarily two different parts of it. They are both abstractions. And for computing, you need both of those things. But in the models that we create, especially in engineering and so on, I would have said that separation, nouns, verbs, and so on, is not necessarily a good way to talk about it, other than we have facts or pieces, and we have things that we do to them. So that notion certainly comes out. But I don't think it strongly comes out as being the core, let's say, of abstraction.
Thank you. We have one more question. We actually have a lot of conversation happening on Piazza on this. There are people responding back. I wish I could, you know, turn my desktop and show you what's happening. It's very exciting when the audience themselves help each other out and they give them their point of view. It's probably the best form of online interaction. But Diane Davis, Diane, hi. Two of the latest ideas in education are the maker-based and project-based learning. I am so sorry, that's my phone. Jeff, would you please read the question?
Which Jeff? You mean me, Jeff? So actually, I can read it here. So two of the latest ideas in education are the maker-based and project-based learning. Do you think that introducing these early in a child's education would help them better develop and formulate abstractions? Makerbased. I'm afraid to say, I mean, as I said, I'm not a cognitive psychologist, and I would be afraid to express an opinion. I mean, I can't imagine anything wrong with either of those two. I mean, I think there can only be positive things to do, to have children actually trying to perform projects early and making things. And so I mean, I don't even know enough about the particular learning techniques to be able to say. But for me, from what they seem to be describing, can only be a good thing. As to whether they particularly help abstraction, I don't know. Problem solving, I mean, is again part of this. So one of the objectives of doing and actually performing all of these abstractions is to solve a problem. Whether it's, as I said, a human problem in the family, politics, law, whatever it is, or whether it's actually trying to create a program to solve a problem. So any notion which helps you to work through and produce a result has to be a good thing. And I believe that you would be, as part of this, practicing some part of abstraction. But more than that, I have no idea what to say.
And we have one last one from Richard Roberts. Only Javier Sotomayor has jumped over 8 feet. You can train and improve your ability to high jump only within the scope of your innate physical ability and the age at which you begin your training. Is there a critical period, an age in which formal operation must occur to maximize one's innate ability? Fabulous question.
Yes, absolutely. Good question. Yes, I don't know. I would say that you actually, in some sense, I mean, since, again, I can only talk from totally personal experience, and I know Piaget did all his experiments on his own kids, but have since had all sorts of criticisms and so on because they weren't typical of all children. But again, the feeling that I have is that I can see that trying to practice and trying to introduce problems and problem solving and activities from what I think the earlier question to do with maker-based and project-based learning, I can only think that this is a good thing, starting very early with children. I mean, they do this with putting blocks one on another, but they have to have passed certain stages in order to get there. I mean, the difficulty is moving from a physical world, from the world in which they're actually moving blocks, into this hypothetical world, where they can actually start to talk about things in terms of not actually being able to represent the physical objects themselves. So when they move into this hypothetical thinking, I think that, and the more practice one has in that, it's only good. So I don't know whether, for instance, things like debating is something which is practiced. So the notion there of putting people in situations where they have to debate a topic, for me, also has this notion that you have to think hypothetically, and you have to be able to start to present an argument for something. All of these, I believe, are good training towards being able to think abstractly, to be able to put yourself in this other world and then relate it back to the real world. So I think early on is good, but I couldn't say which particular age. I mean, Piaget said around 12 years old. I am afraid to say I just don't know. But I do believe you can, let's say, and all the evidence seems to be that you can train people and improve their abstraction abilities, so that I do believe that we should be doing more, and I think that we also should be both performing it and then reflecting on it, to discuss it and assess it, to make people conscious of what they're doing, so that they actually get better at it. Because I think that if in a class, for instance, we were discussing, let's say somebody created some model or some abstraction of something, others criticized it, and then we discussed what might improve it and what might actually not be a good particular approach, would all help students to understand what is a good process of creating these abstractions. And I think that is something which is perhaps rarely done, and that's perhaps something we can do more.
Well, thanks, Jeff. That was really personally helpful to me. I know many of our teachers will benefit much from all your comments. So in the same way that your paper has been long-standing and helping many others, I think that this talk itself will be highly viewed, and especially in the effort here with the CS Principles course, we're going to make sure that a lot of people know about it and come back and watch this video. So thanks so much for coming on with this. You, again, hold the record for our long distance, most difference in miles between the speakers. So thanks for coming on, and we really appreciate all of your help with this.
Thank you very much for inviting me. I've been delighted, I have to say. It's really been a pleasure.
Okay, thanks to everyone for watching, and we'll put this up on YouTube, and look forward to chatting with you more on Piazza. And please continue the discussions that Jeff helped to initiate, and we'll see you all online. Thank you.